The next most complicated case for us to talk about is talking about multiple independent variables existing for the chain rule. So suppose for a moment that we have z, which is a function of x and y, and that x and y themselves are functions of two variables. Now we typically use t as a parameter, and so we stick close to it in the alphabet when we want to define a second parameter. So we'll use s and t, but I would say probably the most common way that you've seen this represented as a function of two variables has been in polar coordinates, where x is a function of both r and theta, and y is a function of r and theta. We're going to stick with s and t for the sake of consistency. I think that rhymed. That's awesome. So what we have here is that z is now a function of two variables, and that x and y are now functions of two variables as well. So when we consider all of the possible derivatives of z with respect to one of our independent variables, we can now consider the partial derivative of z with respect to s or with respect to t. So with that in mind, these are now partial derivatives rather than ordinary derivatives. So to get from z to s, there are two paths possible. We can either go z to x and x to s, and x to s, or we can go from z to y and y to s. Z to y and y to s. So it looks very similar to the expression that we had with only one independent variable. The difference is we now have partial derivatives, since x and y are now functions of multiple variables. Similarly, if we wanted to talk about the partial derivative of z with respect to t, we can go from z to x and x to t, z to x and x to t, or we can go from z to y and y to t, z to y and y to t. Now you'll notice that if we were only doing one of these or the other, we'd be responsible for taking 4 derivatives, but when we do both of them, we are responsible for only 6 derivatives. This is due to the fact that the partial derivative of z with respect to x and y is going to get recycled in these. So this is starting to make a stronger case for not simply substituting in the s and t and taking partial derivatives, but actually keeping it all separated. So as an example for this process, I would like to consider, I'd like to find the partial derivative of z with respect to x and the partial derivative of z with respect to t for z equals the natural log of 3x plus 2y, where x is parameterized as s times the sine of t, and y is parameterized as t times the cosine of s. So what we'll do is we will start by copying down our expression for the partial derivative of z with respect to s. We said on the previous page we can go from z to x and x to s, or we can go z to y and y to s. Or if we wanted to tree diagram this, of course, we can do that to help us visualize. So with that in mind, partial derivative of z with respect to x. Derivative of the natural log will be the reciprocal function, and the derivative of the inside, partial with respect to x, will give us an extra factor of 3. So this will be 3 divided by 3x plus 2y times the partial derivative of x with respect to s. This would be considered s times a constant, as we'll be treating t as though it's a constant. That derivative will just be the constant, plus the partial derivative of z with respect to y. Similar to what we saw for x, we are going to see an extra factor of 2 pop up from the chain rule, so this derivative will be 2 over 3x plus 2y, times the partial derivative of y with respect to s. Now we're going to treat this as a constant times the cosine of s. That derivative will be the negative sine of s. The constant multiple we simply ignore. Now if you are interested, and I am in this case, since they already have a common denominator, let's go ahead and put them all over the same denominator. So we'll see a 3 times the sine of t, and we'll see minus 2t times the sine of s. We'll keep that s inside parentheses so it doesn't look like we're committing any sins. Sorry, guys. Sorry. Actually, you know what? I'm not even remotely sorry. It's fine. It's fine. This is fine. So, for the partial derivative of z with respect to t, let's go z to x and x to t. So, partial derivative of z with respect to x, which we already calculated, and the partial derivative of x with respect to t. Then we could also go z to y and then y to t. So, partial derivative of z with respect to y times the partial derivative of y with respect to t. So, two of these derivatives we've actually already calculated. Partial of z with respect to x, that was our 3 divided by 3x plus 2y. Here's a new one though. Partial derivative of x with respect to t. We're going to treat x as though it is a constant times the sine of t. Constant multiple we ignore, and we differentiate the differentiate the sine of t to get cosine of t. But at what cost? Plus the other partial derivative that we're going to recycle from the previous partial derivative times the partial of y with respect to t. So this would be considered a variable times a constant. That derivative will simply be the constant. Now once again, these are all over the same denominator, so let's go ahead and combine to one single fraction with a denominator of 3x plus 2y. First term will be 3 times s times the cosine of t plus 2 times the cosine of s. So those would be our final answers for the partial derivative of z with respect to s and with respect to t.